We launch a projectile with some speed and at some angle with the horizontal, and we know from observation that it will follow this kind of a trajectory. But what we really need to know is, at a given time t, would the projectile be here? Would it be here? Would it be here? So in other words, we would want to know, at any given time t, what would be its x displacement and what would be its y displacement. And knowing the x and y displacement, we would be in a position to precisely locate the position of the projectile. And to begin with, all we know is this velocity vector v. Let's observe the velocity vector as the projectile is in flight. And it is very clear from here that the direction changes at every instant. Now let's go over this slower. You can see that as the projectile rises, the angle made by the velocity vector with the horizontal reduces, and as we reach the very top, the angle goes down to 0, and at that time the velocity vector is parallel to the ground, with theta being 0. And as it falls back again, the angle begins to increase, and when it lands along the same horizontal surface, the launch angle and the landing angle will be the same. So we know that the direction of the velocity keeps changing along the path. But what about the magnitude? Does that change also? It is difficult to estimate from this animation whether the speed changes or not. But experimentally, it is established that as the projectile moves higher, the speed reduces. So at the launch point, the speed is the highest, and as it reaches the very top, the speed is the least, but is not 0. Again, as the projectile falls, at the landing point, its speed is the same as that at the launch point, provided the launch and landing are in the same horizontal plane. So this motion seems a fairly complex motion, where the velocity changes in both magnitude and direction, and besides, the path is no longer a straight line as in rectilinear motion, but is a curved motion. So how is it possible to determine the displacement of the projectile at any given time t? To make the analysis simpler, we resolve the initial velocity vector into its components along the x-axis and along the y-axis. Vx, its component along the x-axis, is v cos theta, and Vy, its component along the y-axis, is v sin theta. But how would resolving this vector into components help us in our analysis? Now this concept is very important in projectile motion and will help you simplify the problem. We can solve for the x and y displacements independently. What that means is that we work in 2 steps. In the first step, we use the initial velocity and acceleration along the x-axis and completely ignore the y-axis. This way, we determine the x displacement. And in the second step, we use the initial velocity and acceleration along the y-axis and completely ignore the x-axis. and this way we determine the y displacement. Once we find the x and y displacements, we have the precise position at any point in time, and as we dive further into the lessons to follow and solve more problems, we will find this concept easier to digest. This concept presents a very powerful technique to understand and analyze projectile motion. The velocity of a projectile changes in magnitude and direction all along the path of the projectile. To make the analysis simpler, we resolve the velocity vector into its components along the x-axis and along the y-axis. The displacement or motion equations can be applied independently along each axis, one at a time, by ignoring the velocity and acceleration along the other axis.